These here are called tetrapods, or wave-breaking blocks. They're wave breakers, so they help absorb the energy from ocean waves and protect the shoreline from erosion. Here's some models of them. You can find these all around Japan, stacked up on shorelines. These ones here are the closest individuals to my house that I've run into. They help break the water energy from a nearby water gate, protecting the artificial island that's under Haneda Airport. These ones are the smallest ones that I've seen in the wild. A few meters perhaps. But you can find very large ones as well. This one is 80 tons, I believe. The shape is really interesting. They don't want to stack in any sort of orderly way, and instead they want to tangle together when you pile them up. I think that's why they're a great shape for wave breakers. Now, examining these creatures, you quickly realize that they have many symmetric features. 4 axes of symmetry, perhaps. And that makes sense. After all, tetrapod just means 4 legs. And each of these 4 legs seems to be a simple cone that's also symmetric in its own right. So to create a model of one of these, all I need to do is create a single cone and then copy it 3 more times. And all of these should be at equal angle to each other. So at a glance you might think that the angle between these was a third of a circle, so 120 degrees I believe. I for sure thought this way in the beginning. But turns out if you spread the legs by 120 degrees, the first 3 go fine, but they end up in a plane. So where does the 4th one go? Does it go upwards from there? 90 degrees there. That's not 120 anymore. Instead, if you take one of them to be the head or the top leg, the remaining 3 seem to bunch up downwards from that. But then I realized a tetrapod is in many ways analogous to a tetrahedron. So you can see that adding a cylinder to each of these 4 faces and growing it outwards would give you a tetrapod. Or similarly, you could think of each of the vertices as one of the arms and grow one out of there. So if this is the case, to find the angle of tetrapod legs to each other, all we need to do is to solve the angle between faces of a tetrahedron, and we should have our tetrapod angle as well. So for tetrahedron, that is easy enough. Just ask Siri for the answer. And it seems to be 109.5 degrees approximately. So that's great. So the angle between the arms is universal to each tetrapod that you could find, but you could still have many different designs by varying the angle that this leg narrows down at. So you could have totally straight tube ones, skinny ones, or very round and fat tetrapod designs too. So looking at these wild ones, I think the angle between the edge of these arms, they seem to meet at a 90-degree angle down here inside of the shape. So let's go to CAD. We should be able to create a tetrapod with very little sketch elements because of all the symmetry that's going on. So let's say our arm is 3 centimeters long and the end face is 10 millimeters perhaps. And these 2 values are also defining features. You would get a different design by changing the ratio between these 2 numbers. So we can create a cone shape up here by revolving this shape. And let's revolve another cone into existence down here, offset by that very important 109.5 degrees. So you could now take these 2 and rotate them around in a cross pattern. Perhaps you can see by the lines in this toy. Or we could just take one of these legs and make 2 more copies of it in a circular symmetry fashion like this, rotating around the top arm's axis. Do you see? So let's chamfer the edges like in the natural samples we see. So here's something cool. Now, how would you ship this tetrapod? Send it to a friend in a box, right? But look, it won't fit in this box. No problem, just turn it on its side so that each of the arms hits a different corner of the box. And now suddenly it will fit where it didn't before. I think this comes down to the way tetrahedrons are analogous to cubes in some way. By the way, printing these very organic, smooth shapes seems like a hard thing to do with a 3D printer, because there seems to be no way to lay them down on your print bed. But you can print them in halves, just like this, and glue them together later. You can split them in many different ways and it'll end up being a mirror image most of the time. Or, it turns out if you stand one on its leg edge like this, the overhangs aren't too bad to print. So you can do it. However, real tetrapods are not plastic, they're cast out of concrete, so let's create a mold for one. Because of all the symmetries going on, I only need to create this one corner of the mold, and I can copy and mirror that later to create the rest. Now it's going to be a negative mold, so I subtracted tetrapod shape from this block, and now comes the mirroring and the copying. I can get the rest. So my idea is to make it fold together like this, with this little living hinge here, just like that Mars lander. So here we go, tie it together with a zip tie, mix up some gypsum plaster and pour it in. Try not to miss the mold. The plaster replicates these layer lines very nicely, it's super cool. And the real specimen in the wild also tend to have these sort of mold lines in similar places. So I think this is close to how they're born in the wild as well. So these little tetrapods will help protect my herbs from erosion.